So we talked about the torque and the bending moment being the same thing. Now we're going to look at rotation. So essentially, if I have this object and I've applied a force at a particular distance, I don't resist it, it's going to want to rotate like so. Before we actually think about this distributed object, which is a little bit more complicated, we're going to look at the point mass. So anytime in mechanics or physics you want to make things simpler, life simpler, you kind of approximate it or kind of do an assumption or you kind of deal with a point mass. So essentially imagine that you have a point mass like this and then the point mass is going like this and maybe it's accelerating, decelerating, whatever you may have. So it's kind of going about this particular circle. This W over here is going to be my angular rotation. The angular velocity is actually a vector and it's actually pointing out of the screen. So essentially, if this is my x-axis, this actually comes out of the screen like this. So because I've applied the right hand thumb rule, so this comes out of the screen. And then this is the direction it's actually occurring in. So anyway, so imagine I have these marked out. I have this position, which is a vector. It's going to be given by r vector. You have the omega, which is the angular velocity, is also a vector. The velocity, the vector velocity, I'm going to put a bar to denote a vector, is given by omega, again a vector, and then we're going to do a cross product here. So just to make things a little bit more differentiated, I'm going to call or use this for my cross product, and then I'm going to do W cross R. So this is the vector form of my velocity. So again, if you kind of are becoming experts now in the right hand thumb rule, so basically this is pointing out of my screen, this is in this direction, and you will notice your velocity actually comes like in this direction. So this will be my direction of the velocity. So why are we interested in velocity? Is because my force is defined as the rate, excuse me, the acceleration is the rate of change of velocity. Again, acceleration is a vector, you need to be aware of that. And then my force is mass times my acceleration, which is mass times the rate of change of velocity. So my F, which is a vector like here, is actually equal to mass and then times d, and then this, keep in mind this is a vector, and then divided by dt. So there would be a force if either the magnitude or the direction of the velocity changes. So this is really important. So if the velocity is constant, so the object will just keep going over like this, so you'll end up with an object like this, and then it just keeps going so on and off the sheet. But in order for it to go in a circle, its direction needs to change. So you actually need to apply a force kind of which pulls it and then deforms the velocity in this direction. So essentially that is important to keep in mind. So basically what happens is we're not actually going to derive this, but what will happen is because the way this is set up, the direction, rate of change of direction of r is actually omega times r. So we basically get F would be two components, basically one basically change in direction of velocity. So essentially after a small time the velocity is going to be pointing in this direction. The change, if you look at this, is going to be initial velocity is like this, the final velocity is like this. The little change is actually going to be kind of towards the center. So I'm going to have a radial component of my force, which is going to be minus m r, and then this times omega squared. So this is going to be along, r vector. Because of my negative sign, r is pointing outwards. Because the negative sign, this basically says the force is going inwards. And the other thing we have is that the velocity magnitude could potentially change. That would correspond to the angular acceleration. So if I, what I'm actually concerned with is the torque that would be needed to cause my angular acceleration. So if you recall, my torque is actually force, distance times force times cosine. But if you do a vector product, this basically becomes r cross f, right? So I'm going to ignore the vector product, so but you can actually do it properly in a vector format. But basically what happens is my torque, my force is basically due to m, and then velocity is r times omega, right? The magnitude change is going to be omega dot. So this basically becomes, I have this r, so I'm just going to drop the vector notation. So t becomes r from here. This is from here, and then my force is another r, and then we have, then you're going to be differentiating here, so this basically becomes omega dot, and that's pretty much it. So if I rewrite this, and then we left the mass, so basically times mass. So this, if I rewrite, this basically becomes, looking for space, so let's do this over here. So this basically becomes my m r squared, and then times this omega dot. So this basically becomes omega dot, or this is also called as alpha, the angular acceleration. So if we look at this particular view thing over here, this part is kind of a function of the object. So it kind of it is dependent on the mass as well as how far the mass is from the point of rotation. So what we do is, this is known as the mass moment of inertia, and it's denoted by the letter J. So it's important to kind of look at the difference between the two. So this J is the mass moment of inertia, right? So the unit, if you recall, it's going to be mass times a distance squared. So this is going to be kg meter squared. So this is in SI units, so you can figure out the equivalent in different units. This is kind of like a property related to the mass. We also had another moment of inertia, which is I. This is known as the area moment of inertia. So this is actually a fourth power of the meter. So this is basically was meter to the 4. This is used here. This is used for angular acceleration. This is used for bending. And then this is for rotation. So this is important. These are kind of related. So the same object could basically have both kinds of moments of inertia. So you can basically have a beam like so, and then if it's going to be bending, so if I apply a force like this, it's going to want to bend like this. So you would consider the area moment of inertia in this direction. And if the same beam if the same beam is kind of rotating about an axis, say it's axis coming out of the screen, so it's kind of rotating like this, then you would actually also calculate the mass moment of inertia of the beam. So the same object can have both the area moment of inertia and the mass moment of inertia. So the next question is, what happens if you have a distributed or kind of particles all over the place? What we can actually do is calculate the J for each particular object. So basically, if you call it J1 would be M R1 squared, and then you'll have J2 will be M2 R2 squared, and then so on and so forth, right? So if all of these objects are basically part of the same system, we need to add up all of these. So essentially, if I have one object, if I need to apply 10 force, 10 newtons to move it, if I put a second object on top of it, and this needs 10 newtons, this needs 10 newtons, I'm going to apply 20 newtons to move the whole structure. Same thing over here. If it takes 10 Newton meters of force to rotate this like this, it takes, let's use different numbers and say 5 Newton meter to rotate it like this. If I have both of these and I want to rotate it, I need to apply, by superposition, I need to apply 10 for this, 5 for this, so I'd apply 15 Newton meters. Same thing happens here. Because of the effect being similar to mass, you need to add all of these terms. So you'll basically add J1, J2, so on and so forth, and my total J basically becomes summation of Mi, actually it's summation of Ji, but this is going to be summation of Mi Ri squared to how many ever particles you have. So if you have n, so this is going to basically go from 1 to n. If the same thing, it's kind of like a more of a distributed thing like this, and then you have like more particles like this, so on and so forth. What basically back comes is that this integration basically, this summation basically becomes a integration, right? So J would basically be an integral, and then because this becomes dm, so this becomes dm r squared. And then this needs to be done either over the like the whole mass. So this is the formula. So you have the Fr, which is for the rotation, which would be the net force that's actually given by m r vector omega squared, and then this is going to actually be the torque. So this will be the torque is actually going to be m r squared omega dot, and so you're basically summing up over all of these, and then if you do an distributed load, it becomes an integral. You can actually do the integral and get different values. So in this case, you'll basically integrate it from minus L over 2 to L over 2, but there are actually books, or rather all statics books actually give you the formula for the moment of inertia. For this particular case, oh, by the way, I forgot to mention, so we use the letter J for mass moment of inertia. So anyway, for this guy, J is, if you do the integral, you'll find this becomes 1 by 12. This basically should be uniform, all this cross-section area. So it could be any shape. So it could be like so. As long as it's uniform all over, this formula is basically valid. So this becomes 1 by 12 ml squared. And this formula here, so this is basically the rod rotating about its center point. You could have the same thing rotating about the end. So essentially I could have this pen. I could rotate it like this, where the axis of rotation is over here. I could also hold it here and then try to rotate it like this. If you actually tried this, you notice that it's easier to rotate it basically about the center versus here, because the moment of inertia is lower. Conceptually, you can think about it. If you look at this, you're squaring the distance. So the square distance of all of these points are much closer. And then if I move my hand over here, the square distance of this particular point is much larger. So for here, I get the formula J is 1 over 3 ml squared. Right? So again, this also applies for any arbitrary cross section, so long as the cross section remains the same throughout. So basically, so long as it's like this. Actually, erase that. So the cross section needs to remain the same. I'm trying to really hard. Yeah. So the cross section needs to remain the same as long as it goes through. This equation is valid. The next question becomes, what happens if the rod is at a particular angle? So now again, the axis of rotation is here. So it's basically kind of rotating about this axis like this. And we are going to assume that the rod is going to make an angle theta with the axis here. So the previous example, the theta would become 90 degrees. So here, notice that it's as though the whole thing is kind of becoming larger, but you can kind of like project it down. So my actual rod kind of looks like this. And this length basically becomes L sine theta. So if you look at the formula for this, the J here is going to be 1 over 12. And then this becomes M, and then it's L sine theta and then this becomes the whole squared. And then same way over here, so this basically becomes j, this is 1 over 3 m, and then L, I'm going to write over my face, the whole square. Notice that you're squaring the whole thing, so it's either this, or you can think of L squared sine squared theta. So both are equivalent and same, right? So basically the previous example, if you put theta as 90, this term becomes 1, right? And then it reduces to the previous formula that we have. The next important thing that we would usually discuss when it comes to area moment of inertia is what's known as the parallel axis theorem. So parallel axis theorem states that if I want to find the moment of inertia about an arbitrary axis, so we'll call this an arbitrary new axis, I can calculate this if I know the moment of inertia about a parallel axis passing through the center of mass. So if I have this pen over here, I want to find the mass moment of inertia about this axis. What I do is, if I know the mass moment of inertia about this axis, which is passing through the center, and I know the distance between these two, I can calculate the new mass moment of inertia as the old mass moment of inertia plus m t squared, where d is the distance between the two axes. So essentially, if you have the object like this is my j center of mass. The new axis can be anywhere, so the new axis can even be here, it could be in your home, it could be in Pluto. All I need to do is find this distance here, and then I just plug this in this particular value. Note, really important, this is only valid when the original axis is passing through the center of mass. You cannot do this if it's an arbitrary axis. So we're going to really quickly take a look at this and double check. So remember, we had the j end, which is again kind of going from, so like you look at this, you can think of this moving from this point, which is the center of mass, to this end, and this distance is L over 2, right? So we can see if this actually works out. So the j end is 1 over 12 ml squared plus m times L over 2 the whole square. So you can actually do this calculation. So this is 1 over 12, this becomes 1 over 4, and then if you do this, this becomes 4 by 12 ml squared, and then this cancels out, this basically becomes 3. So now you're going to do slightly more interesting thing. So what we're going to do is try to find the mass moment of inertia of the rod about a point which is quarter of the length from one of the ends. At this point, I would like you to kind of maybe pause the video and then try to see if you're able to actually solve this yourself. Okay, hopefully you're unfreezing the video at this point and then trying to calculate this value. So we are actually trying to do this by two methods. So the first method is I'm going to take this beam and then treat it as is. So I'm going to assume that I kind of know the center axis over here. This is going to be at a distance L over 2. So this JCM, this is 1 over 12 ml squared. So what is this distance between the two axes? So this distance is L over 2 minus L over 4, so this becomes L over 4. So this is my D, excuse me. So this is basically equal to D. So my J axis is going to be JCM plus M, and then D I substitute as L over 4. Really important, so this needs to be L over 4 the whole squared. So this basically becomes, I pull ml squared outside, so this becomes ml squared times 1 over 12 from here, and then this becomes 1 over 16. So this becomes, it should be, what is it? Not everybody at once. Actually, I can't hear you over YouTube, but this basically becomes 7 by 48 ml squared. Right? So as a bonus, what we're going to do is try to kind of do the same problem, but actually splitting the beam into two parts and then see if you get the same number. Again, remember, this came out to be 77 by 48 ml squared. So this beam, what I can do is I can basically think of it as being a small beam like this, rotating about its end, plus another bigger beam rotating about the same end. Need to be a little careful over here. When I cut the beam over here, this length becomes L over 4. This mass also becomes M over 4. This is important. Right? Same way for this guy, the length is 3L by 4. This mass is going to be 3M by 4. So again, I can calculate the J for each of this and then do the total. So my J becomes J for this guy, which is basically M over 4. Sorry, it's going to be 1/3. It's going to be 1/3 ml squared, but this M needs to be here. This becomes M over 4. And then this is L over 4. And then the whole square. And then plus 1 over 3. And then this becomes 3M by 4. And then this is 3L by 4. The whole square. Now, if you actually calculate this through, this is basically 1/3 that comes out. This is going to be 4. This is going to be 16, 64. And this is going to be 3 times 64. And then the top is going to be 9. And 9 times 3 is 27. You get 28 by 64 times 3. And then if you actually kind of cancel out the common terms, and then if you do this properly, so you should actually get this. Should I write over my face? Sure, why not? So you should actually get this to also be 7 divided by 48 ml squared. So again, I want you to try to kind of pause the video and then test out this yourself. So this concludes our brief discussion on mass moment of inertia, area moment of inertia, buckling, and then rotation. Just to quickly recap. So bending and torque are kind of like related to each other. So if you have it at a particular distance and it doesn't rotate, it becomes torque. If it does rotate, it becomes it becomes a torque. If it doesn't rotate, it's actually a bending moment. And then we calculated basically really quickly about how the bending moment is related to the area and area moment of inertia. Then we talked about buckling, which is kind of a phenomenon that occurs in compression, and it's actually related to the bending of the beam. So it's basically an interaction between kind of a deflection and the bending. Finally, we talked about rotation and mass moment of inertia. So the area moment of inertia, we said, had the unit of meter to the 4, and then we typically use the letter I. The mass moment of inertia, so this is basically going to be kg meter squared. Here we'll use the letter J. Some books actually use the same letter I, so we're going to avoid it here because it leads to a lot of confusion. So make sure if it's rotation, mass moment of inertia, you always use J. Thank you. So this basically concludes our presentation, and thank you for watching the video.